Alrighty, we're going to start lesson chapter 7, talking about confidence intervals and sample size. As you'll notice in your notes, it actually goes from 7.1 to 7.5, but if you look at the syllabus, it's 7.1 through 7.4. All they did was kind of split 7.1 into two different sections, and then the rest of them are going to be off by a section. So when we talk about 7.1 and 7.2 in your syllabus, it'll really just be 7.1. But in your homework, they have homework for 7.1 through 7.5. So the same topics, it's just they split this first section into two sections and they were pretty much on the same pace. So this chapter will actually be five sections. The first one just being talking about confidence intervals, really just giving that definition line before we move into the meat of the topic. All right, so again, we're going to be talking about confidence intervals and sample size. What this basically means is, as a statistician, when you do your math, they basically want you to be confident with a certain percentage. Most of the times, they either want a confidence level of 99% or even 95%, and even some, maybe 90%, confident that your mean sample will fall in a certain range where the population mean will fall. So basically, you do a sample, and then with a certain confidence interval, you're like, all right, the population mean will fall somewhere in this based off my sample means. And that's kind of really what a confidence interval is. But let's put it into writing and definitions and some examples, so you actually have some things to go with your homework as well. So again, in inferential statistics, we use a process of estimation, estimating the value of a parameter from data attained from a sample. For instance, for each dollar you pay in county property tax, 22 cents covers the cost of incarcerating prisoners. This is from Pittsburgh City Paper. 8% of people surveyed in the United States said that they participate in skiing in the winter times. And this is MRE Sports. So basically, again, what they're doing is we take a sample, and then from that sample, we're estimating what the entire population is probably doing. And then we usually can have a confidence level that the population will probably fall within a certain range within that. These results were obtained from data collected from samples of large populations. So these values are estimates of true parameters. So depending on how big our sample size is, gives us a different kind of confidence. The larger the percentage of the confidence interval you want, the larger your range is going to be. The smaller your confidence interval is. So, like for instance, if you want a 99% confidence interval, your range is going to be a little bit larger to give you a little bit more confidence. If you want a 90% confidence interval, the range of where you think your population mean is going to fall. It's going to be a little bit smaller because you have a little more wiggle room. Because you're like, well, I was 10% off as well. So things to look at as we move on through this chapter. All right, so common assumptions must be met before valid conclusions can be made. Some of these assumptions are the samples are randomly selected. So that is what we're going to be assuming with most of our data, unless otherwise told. The sample size must be at least 30, or the population must be normally distributed. If we know it's normally distributed, how big the size is not going to matter. If we don't know if it's normally distributed, then it needs to be at least 30 samples or more. You can use a histogram to see if it is approximately bell-shaped. We did this in the other videos. Not my favorite. And we can check for outliers. I like the outliers way and using the formula to see where it falls. That's my favorite, but if you are better with the histograms, it's almost like when you are solving equations of systems, you have the graphing way or the substitution or elimination way. Graphing doesn't always give you the exact answer if it's a decimal. So you can go those three different routes. I prefer formulas. All right, so that's the introduction to the chapter. So let's get into 7.1. Again, a little bit different from what's in your syllabus. This one's just going to be talking straight up what is confidence intervals. So in our first objective, we're going to find the confidence interval for the mean when the standard deviation is known. So the definition of confidence intervals is a confidence interval is a specific numerical value estimate of a parameter, the best point estimate of the population mean, again with the little sigma, is the sample mean, again with the X. So remember the Greek and Roman letters. The sample mean is used instead of the median or mode because means of samples vary less than other statistics when many samples are selected from the same population. So we'll be focused. There's a lot of the central tendencies between mean, median, and mode. You'll be focused on the mean averages of all these different samples to kind of guess what our population mean would be. A good estimator have the following properties. It's unbiased. The expected value of the mean of the estimates obtained from samples of a given size equal the parameter being estimated. So there is no wiggle room between the sample means and the population mean. Everything was random. Wasn't like a convenience thing. It was all unbiased, which is really hard to do these days. Remember, even our life experiences kind of lead us towards different conclusions. The second thing is consistent. For a consistent estimator, as a sample size increases, the value of the estimator approaches the value of the parameter that is estimated. So the larger my sample size gets, the closer and closer I get to my actual parameter. Meaning, if I have, I don't know, let's take a school of 500, right? And I take just 30 people and I find out the confidence of their football team, right? So I take 30 random people. It's all unbiased. I ask their opinion. I write it down. They either do or they don't. Think they're going to be successful this year or whatever the question, whatever the situation is. And I get an average and I go, you know what? Out of 30, 15 of them thought the team's going to do good. So I can say, well, 50% of the school is going to do good. But the larger I make my sample size, the more accurate my mean will be. Maybe it was closer to 40%. So I'll start seeing that 50% get smaller and smaller as I add more to the sample. And then the third thing is relatively efficient estimators. Of all of the statistics that can be used to estimate a parameter, the estimate has the smallest variance. Remember, variance just means the spread of your data. The smaller the variance, the more accurate our results are to the mean. All right, confidence intervals. Statisticians prefer to use interval estimates because the sample means are somewhat different from the population mean due to sampling error. So like I said, I grab 30 and I say 50%, but I'll have a confidence interval of a certain percentage. And I might say, all right, I think the population mean is going to fall between 40 and 60%. Right? I got 50, maybe I think it's plus or minus 10%. So I think the entire population is going to fall between 40 and 60, and then we give it a confidence. Maybe I'm 90%, maybe I'm 99% confident. And I'll show you the math behind it as we do the work through as well. All right, so a definition. So interval estimates So an interval estimate of a parameter is an interval or a range of values used to estimate the parameter. The estimates may or may not contain the value of the parameter being estimate. So we have a certain confidence that we're like, all right, we really think our population mean is going to fall between these two values, but it might not. That's why in statistics, you're never 100% accurate. There's always a chance that it falls outside. So a degree of confidence must be assigned before an interval estimate is made. This is a percentage stating how confident you want to be that the individual does contain the true population mean. The interval the interval for 95% confidence is not as wide as the interval for 99% confidence. Again, the larger that percentage, the wider your interval. Because if you're going to be 99% confident, then I need a little bit more room to make sure I don't have anything fall outside it. If my confidence level is not that large, I can get pretty darn narrow. So if I do make a mistake, I'm like, well, I was, 15% off that, so that's kind of so have that idea. The larger the percentage, the larger the interval. The smaller the confidence, the smaller the interval. So to increase the confidence that the true population mean is in the interval must be made wider. So if I want a more confident interval, I need to have a wider range. All right, so definition of a confidence level. So the confidence level of an interval estimate of a parameter is the probability that an interval estimate will contain the parameter, assuming a large number of samples are selected and the estimation process on the same parameter is repeated. So again, the wider my range, that 99%, I am basically stating I am 99% confident that the population mean will fall in this range. Or if I'm 90%, then I'm 90% positive that the population mean is going to fall in this. So again, we're never 100% because there's always that chance it falls out. All right, then the definition of a confidence interval. So again, a confidence interval. So you have a confidence level, that's the percentage, and then you have a confidence interval, which is specific interval estimate of a parameter determined by using data attained from a sample and by using the specific confidence level of the estimate. So we're going to use that sample mean, and we're going to try to use that to help us come up with an interval. Again, I came up with that 50%. Maybe my interval is between 40 and 60%, depending on how I do the math and how confident I want to be. All right, so the interval estimate is based on what we call the central limit theorem. We saw this in the last chapter. That states that when the sample size is large, approximately 95% of the sample means of same size samples taken from a population will fall within a plus or minus 1.96 standard error of the population mean. That is, the population mean will be plus or minus 1.96 times the population standard deviation divided by the square root of the sample space. Remember that the z value that separates the middle 95% from the outer was 5%. So therefore, there's 2.5% on each side of the normal distribution are then the critical values of plus or minus 1.96. So this would be what we call the z-score. Right? And this is what we did at the very end to determine what is the z-score at 95%. And we saw that it was a plus or minus, basically almost 2 standard deviations of our data. So when a specific sample mean is chosen, there is a 95% probability that the interval of the population mean plus or minus 1.96 of the population standard deviation divided by the square root of the sample space contains this mean. So if I'm trying to guess where my population mean is, I can have this range. But if I have the population mean, then I can plug it in with this. And now I can say with confidence that the sample mean that I pull will fall within this range as well. And then there's a 95% probability that it will, but then there's that 5% that it might not. So again, a probability that an interval will fall between the sample mean plus or minus the 1.96 times the population standard deviation divided by the square root of the sample space will contain my population mean, right? So if I have a sample mean, then I can do this, and then I can say with confidence that my population mean. So it can kind of go both ways. If I know my population mean, then I can say with confidence that a sample mean will fall within that. If I have my sample mean, I can say, all right, with some confidence, I think that my population mean will fall between these two things. So another way to think about this is I can take my sample mean, subtract and add the 1.96 times the population standard deviation divided by the square root of the sample size, and I can assume my population mean would fall between these with a 95% probability. Again, there's that 5% that it could fall outside. Maybe the sample space I get's a little skewed in the sense that maybe it's, I don't know, maybe I picked everyone on the football team or something, Even though it could be completely random, it could have completely randomly selected all of those. All right, so we take this and they are constructed for all possible sample means. So again, the sample mean, 95% confident is what, so 95% of the interval will contain the population mean. So again, we're 95% confident that the population mean will fall between this, or vice versa. I'm 95% confident the sample mean will fall between what I'm assuming is my population mean. Depending on what data you can get, you can go both ways with it. All right, so the confidence interval, or sorry, the confidence level determines the critical values of your Z that are used to find the confidence interval. So using Appendix A, Table E, won't use technology, to find the critical values of our plus or minus the Z-score of the alpha divided by 2 for different confidence intervals. The alpha represents the total area in the two tails. So alpha divided by 2 represents the area in each tail, the confidence level. And I think this part is what's missing. So this part should say is 1 minus the alpha. That would be the confidence level. Thus, when 0.01, then 1 minus the alpha would be 1 minus 0.01. So that'd be a 99% confidence area. So this is basically what you're doing. So if I take that 95%, right, I want a 95% confidence interval. So what I would do is knowing that this is my confidence, my alpha would be what falls inside the two tails. So if I do 1 minus 0.95, I actually get 0.05. This is alpha. I then have to divide that by 2. So I get now 0.025, right? That would be my alpha divided by 2. So remember, I'm finding the two tails, so I just need to find one of the tails. So then I would use the appendix A at 0.025, and I would go to where it is, and I would say, hey, that's negative 1.96. Well, if it's this one, I now know it's symmetrical, so I can say it's plus or minus 1.96. So same concept here. If I wanted a 99% confidence level, I would need to go to 0.01, divide that by 2, so that's 0.005, I would need to go to this and figure out what its plus or minus z-score is. I don't know on the top of my head. Actually, I do. It's actually 2.58, right? So therefore, if I want to be 99% confidence, notice that I'm now multiplying by plus or minus 2.58. I'm being a little bit more out there because I want to be a little bit more confident. So I need that range to be a little bit more. All right. So margin of error. So margin of error is represented by capital E, and we find it by finding the z-score of that alpha divided by 2. So these are the z-scores for those specific values. And then we would multiply by the population standard deviation divided by the square root of the sample. This is called the margin of error. This gives us that range of that plus or minus outside what we think is the actual, but it could be a little to the right, could be a little to the left. So it's called a margin of error, or it's called a maximum error of estimate. It is likely different. It is likely difference between the point estimate of a parameter and the actual value of the parameter. So with a margin of error, we can state that, all right, I think we're going to be 10% off our actual mean. That would be your margin of error, plus or minus 10% on both sides. If that's what we're calculating, go back to that example I told you about the football. All right. So that's what that margin of error basically would do for us. So to kind of wrap this up, so the margin of error depends on the following factors, though. The population standard deviation, because it's inside the formula. So the normal distribution can be used to find the confidence level when the population standard deviation is known. The confidence level, how confident do we want to be? So if a large number of intervals are constructed, the confidence level represents the expected percentage of interval that would contain the parameter. And then our sample size. Is the sample size large enough? The margin of error decreases as the sample size increases. The larger we have in our sample, the smaller our error can be. Right? So that's pretty much an introduction to confidence intervals and sample size. So this is the 7.1 that will show up in your homework. And then the 7.1 that's on the syllabus will be our 7.2, which will then represent in the book, and then will be pretty much the same in the syllabus. All right, so if you have any questions about how confidence interval is displayed, reach out, let me know. I can go over some more details. Other than that, I'll see you in the next video.